Good morning. I just wanted to do the same problem, but maybe show you a different approach to it. All right. You'll recall the problem is you're driving down the road, you see danger. It takes you a half a second to react, and then it takes you another 3.5 seconds to actually slow down and stop. So we have a velocity graph that looks like this. And we could just do the same thing using equations. So I prefer showing where the equations come from, and it turns out the equations come from the graphs anyway. And so I would start with a velocity graph and just say, look, if we want an equation for the motion of the car before the brakes were applied, all right, fine. That area is displacement. Displacement is going to be our velocity, this number, times our time, which in this case is 0.5 seconds. Move this down a little bit. It's kind of in my way. So that's 0.5 seconds. And this is 4 seconds because the 4 seconds has to be 3.5 seconds of slowing down. And that's pretty much it. I can make it look a little better. Delta x, change in position, which is displacement, is our final position minus our initial position during that first half second constant velocity period. And that's equal to velocity times time. And that means that final position is equal to initial position plus velocity times time. And this is actually a vector equation. Meaning that our initial position vector and our velocity times time, our velocity vector scaled by time, that should equal my final position. So if this is my final position vector, I got the initial position vector, my x naught vector, adding to my velocity vector that is changed in size by t. T just multiplies by my velocity vector to make this vector arrow bigger or smaller. So this is a graphical representation of this equation here. And I guess you could get cute and put numbers in. Let's make life easy and make our initial position 0. So then final position of the car after at t equals 0.5 seconds is going to be, what, 25 meters per second times 0.5 seconds. So the final position of the car is going to be, what, 12.5 meters at t equals 0.5 seconds. Okay? So that part of the problem is done. Let's go back up and deal with the more complicated motion, the constant acceleration motion. Okay? So now I just want to talk about this part of the motion here. The equation of this line is going to be velocity equals whatever that slope is, and since that's a velocity graph, the slope is our acceleration, times t, and acceleration has direction, okay, plus whatever our initial velocity was at the beginning of that constant acceleration time period. So final velocity at the end looks like it's 0, okay? So you have 0 velocity at the end. This is going to be 0. Your acceleration is got to be the slope of this line. So let's find that. A equals change in velocity divided by change in time, okay, which is going to be v final minus v initial over t final minus t initial, okay? So A is going to be, it's got to be a negative number. It's going to be 0 velocity at the end, so that's my final, minus 25 meters per second in the beginning of that constant acceleration time period. So the 25 meters per second is the velocity at half a second, really. And it's not necessarily at 0 seconds, it's at 0.5 seconds. And the beginning time is 0.5 seconds, okay? I can make that look a little better. So it's the final velocity at 4 seconds. So why don't I write it that way? It's the velocity at 4 seconds minus the velocity at 0.5 seconds, okay? And that's going to be the time, 4 second time minus 0.5 second time, right? So 4 seconds minus 0.5 seconds. So this is going to give me a negative acceleration. It's going to be 25 divided by 3.5. Let's see what that is. 25. That's negative 25 divided by 3.5. 7.14. Okay? So it's negative 7.14 meters per second per 1 second. Now, what does this mean? Every second that's that second, the velocity changes by negative 7 meters per second. I'm forgetting about the 1400ths of a second. I figure that doesn't really matter that much. All right. Let's go back up. Any second now. Just waiting for the computer here. Now that we know an acceleration, we should be able to use the equation for velocity. All right. So let's see if we can do that now. Just got to scroll up a little bit. Having a little trouble here. I guess I could just write it right here. If I can get this thing to write. Cool. So our velocity equation is v final equals at plus our initial velocity, which is actually at 0.5 seconds. Okay. And we decided that our final velocity at the end was 0 because the car stops. Our acceleration looks like it's, what, -7, right? -7, and I'll just add the 0.1 right now, meters per second squared, okay, times t, okay, plus our velocity at half of a second. So we could use this equation to find the time it takes to stop. I think we know that already. What are we looking for? It says, from the velocity time graph, determine the acceleration once the brakes were applied, okay, and then determine how far the car goes. All right, well, this equation isn't going to tell us that. This equation won't tell us how far the car goes. We need an equation for displacement. And you'll recall that the area under your velocity graph is your displacement. Okay? So, looking at that triangle above, displacement is going to equal the area of the triangle, 1/2 the velocity in the beginning, that's at 0.5 seconds, is the height of the triangle times the time. So your displacement is going to be 1/2 25 meters a second. And then 3.5 seconds, this is the time during braking. Okay, that's the base of that triangle. Okay, so our displacement while braking is going to be 1/2 times 25 times 3.5. All right, so let's try that. 0.5 times 25 times 3.5. And that's going to be 43.75. Okay? Now, if you add this displacement to the displacement we got over here, which was 12.5, you should get the total displacement, which is the same thing we got before. So it's 43.75 meters plus 12.5 meters gives us 56.25 meters. So that's our total displacement. That's the total distance traveled while the total change in position before we started slowing down and then during the period of slowing down. Now, there are other ways of doing this. If you want to just use an equation, you can use the equation delta x equals 1/2 AT squared plus V naught T. Okay? And if you watch the post-lab notes, you'll see how to get this equation. But it's sort of more complicated, so that's why I'm sticking with the graphs. Anyway, there are other options too. You got another equation in your post-lab notes you could use, but again, I tend to like the graphs because they're simpler. I hope you have a good day. Thanks for watching.